Hello there, Andrew Dunkley here, the host of Space Nuts, and it's great to have your company on the latest episode. And coming up, we're going to be looking at a couple of things, very scientific show today. Scientists have done something that only colliding neutron stars can do. They've synthesized new isotopes. I had to practice a lot to say synthesized new isotopes, and I've said it twice without stuffing it up, so I'm very happy. We're also going to talk about a discovery. Recently, we talked about something that's the biggest of its kind we've ever found. We've found the oldest of its kind recently. Now we seem to have found something that is defined as the fastest growing and brightest of its kind. What is it? We will tell you very, very soon. That's coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as always, is the goanna hunter himself, Professor Fred Watson. You've got a visitor in your backyard as we speak.
Yes, we do. Yes, about 1.5 meters long, something in the region of 5 feet. The goanna, which is a lizard-like creature on 4 legs with a long face and a big belly and a tongue that's coming in and out all the time. And very sharp claws, actually. You don't want to mess with goannas because they can do a lot of damage. So this one's pottering around the backyard at the moment as we speak. In fact, I've lost sight of him. I'm not sure, or her.
Yeah.
I'm not sure which way they have gone. But they were there a minute ago. Quite extraordinary.
They've got the pet food and they're gone.
Yeah, that's right. That's what it is. It's the leftover pet food.
Yeah, they can grow to be quite enormous, and yeah, you're right. They can do a lot of damage, and they're very, very. They look harmless enough, but you don't really want to get too close. I've seen a couple of goannas at my parents' place in the years gone by, and they're. Even the smaller ones can be a little intimidating close up.
Yeah, that's right.
Quite amazing and ancient creatures.
Very ancient
tastes like
indeed.
chicken,
That's
apparently.
right.
Now,
okay, never tried that.
Now we've got a couple of stories that we've got to talk about, Fred, and some exciting news in science with the synthesization of isotopes, which was done in a lab using a laser. But this is a sort of a replication of something only colliding neutron stars can do. We better sort of work out what this means, because the scientists involved are very excited about this.
But they are, that's right. So just very briefly, the backstory, what do we mean by isotopes?
Yes.
It starts off with our understanding of how chemical elements differ from one another. There's the chemical elements are actually sort of defined by the number of protons in the nucleus, the atomic nucleus. And so hydrogen, for example, has 1 proton, and it always has 1 proton. Helium always has 2. Iron has 26, just to jump to another number. And so you can't have hydrogen with 2 protons, and you can't have iron with 25. And I'm quoting here from our old friend, the space.com website. But in their atomic nuclei, the atomic centers, protons are joined by neutrons. And so the number of neutrons essentially can vary in a way that the number of protons can't. Protons are charged particles, neutrons aren't. Positively charged particles, neutrons are neutral, hence the name. So if you've got a hydrogen atom with 1 proton and 1 neutron, bless you, then
There'll be another 10 of those.
Okay.
She sneezes once a week. Her record is 25.
Oh, my goodness me. That almost sounds like a medical condition.
You just said sorry.
That's right. No need to apologise. You can't help sneezing. So the bottom line is that adding neutrons doesn't change the element that it is. but it changes the isotope of the element. And so isotopes can vary. And once again, space.com has a nice example. One of the isotopes of iron is iron 54, which has 26 protons and 28 neutrons. There is also something called iron 56, which has 26 protons and 30 neutrons, etc. And so it goes on. So that's what we mean by isotopes. It's elements in a different form, which is governed by the number of neutrons that are present in the atomic nucleus. Now, to cut to the chase, to cut to the story, there are facilities that can actually make isotopes. In fact, I think we've got one here in Australia at the at ANSTO, the Australian Nuclear Science and Technology Organisation. But this particular one that we're talking about, which is at Michigan State University, is a very fancy one, and it's called FRIB. FRIB, that's what the acronym spells. FRIB, I like that, actually. It's a bit like telling lies, isn't it? Oh, you're telling FRIBs. It's the Facility for Rare Earth Isotope Beams. That's what FRIB stands for. And it's basically an accelerator where they can synthesize isotopes. And what they've done is they've synthesized some of the isotopes that we think are created by colliding neutron stars. Now, we can't go and test the insides of colliding neutron stars. What we can see, though, is their gravitational waves, and that's allows us to see some understanding of what's going on inside in that ultra turbulent environment when two neutron stars collide. And neutron stars, of course, are the remnants of massive stars which have got to the end of their lives and collapsed. Usually a supernova explosion that blows off the outer envelope. The center collapses to form a neutron star, where the collapse to a black hole is only stopped by the outward pressure of neutrons against each other. So what the scientists at FRIB, the Facility for Rare Isotope Beams, have done is created some isotopes which have never existed on Earth. That's a pretty big, pretty impressive
That's a bold
claim to fame.
Claim,
a very bold claim, exactly. To be specific, they are thulium-182, thulium-183, ytterbium-186, ytterbium-187, and lutetium-190.
I think I went to school with a lutetium. Yeah.
There's one in every school. I think I went to school with a few ytterbiums, I can tell you. They were rough. Anyway, and the thing is that we think these isotopes are probably involved with the process where colliding neutron stars create new elements, and we now know that the heavy elements, and in particular gold and silver, are created in these neutron star collisions. And so, if you can understand the way the sort of intermediate isotopes behave, then you are going a long way to understanding what the processes are in, as I said, the ultra turbulent environment of colliding neutron stars. If I may quote one of the scientists involved with this, Bradley Sherrill, who is the University Distinguished Professor in Michigan State University's College of Natural Science and head of the Advanced Rare Isotope Separator Department. Says this is probably the first time these isotopes have existed on the surface of the Earth. I like to draw the analogy of taking a journey. We've been looking forward to going somewhere we've never been before, and this is the first step. We've left home and we're starting to explore. So that's a really, a very nice, almost poetic way of putting it. This journey to understand the nuclear processes that go on in some of these very exotic collisions.
Is that the ultimate purpose, to just try and understand a process, or will there be applications that this might be able to be used for if they can, take it to the next level?
Yeah, I mean, you never know what the applications might be. And in fact, I think nuclear physics generally can get, can basically benefit by people understanding how these newly forged isotopes behave. So nuclear physics will be one of the benefactors in this work. One of the other scientists involved in this said it's not a big surprise that these isotopes exist, but now that we have them, we have colleagues who will be very interested in what we can measure next. I'm already starting to think of what we can do next in terms of measuring their half-lives, their masses, and other properties. So it is, it's setting an improved baseline in the whole science of nuclear physics, but it's motivated, as we've just said, by the idea of trying to understand these processes better that take place in collisions between neutron stars.
I'm still a bit confused, though. I mean, I've read through this and tried to absorb it and understand it, and I've taken some headache tablets afterwards. But what do they mean by synthesizing? I mean, they obviously didn't have any neutron stars lying around. Opened a drawer, no, not in there. So what does synthesizing mean?
Well, so I'm not a nuclear physicist, but my guess is that it involves a particle accelerator that is colliding things together to smash them up and synthesize other things. That's essentially what happens at the Large Hadron Collider, for example, on the Swiss-French border, CERN's Large Hadron Collider. It's all about colliding things together. In the Large Hadron Collider, it's generally protons, although they also collide lead atoms, the nuclei of lead atoms, and learn different things from that. So not only when you smash atoms together, you don't just break things apart, you also get reactions taking place that create new things. Okay. So you can synthesize them. Often, though, those elements that you've synthesized only last for a very short fraction of a second. And I don't know in this particular work just how long these newly synthesized isotopes are. So I can actually just say a little bit more, once again, quoting from space.com, talking about those isotopes, thulium-182, etc. These isotopes formed by firing a beam of platinum ions, that's platinum without its electrons, at a target of carbon at the FRIB, the rare isotope manufactory, The isotopes, they say, might not be present in the wreckage of neutron star collisions, but their existence on Earth is definitely a step towards creating those briefly lived transitional super heavy elements on our planet to see if they result in elements like gold. In other words, these are temporary things that only exist temporarily and then might themselves decay to form something recognizable and stable like the nucleus of a gold atom. It's really exciting stuff, I think. It's tinkering around with matter at its most rudimentary.
Yes, yeah, indeed. I think it was also fascinating to try and understand that you talk about stars being the furnaces of all these elements. And
yes,
I think most stars can't do anything more significant than create iron. You need a neutron star to smash into another neutron star to get these... Sorry
about this.
That's okay.
And my phone it's ignoring what I'm saying. Sorry about that, Andrew.
No, that's okay. So you need a neutron star smashing into a neutron star to start creating heavier elements like silver and gold.
That's correct.
Yeah,
that's correct.
And how often do neutron stars hit each other? I wouldn't expect it to be an everyday event, or is it?
It's given the size of the universe and the number of objects in the universe, and the fact that we can now detect these by the gravitational wave signals, I think they are pretty frequent actually. So I wouldn't like to put a number on it, but I don't think you're talking about events that are essentially very rare. And so it's now thought, whereas not very long ago we used to think that all the gold and silver were created in supernova explosions. The evidence that apparently has been uncovered really by the James Webb Space Telescope and other recent facilities have suggested that all of the Earth's gold was actually made in neutron star collisions. And in fact, I think that story was also covered by space.com not very long ago, actually, but essentially in recent weeks. So yes, it's exciting stuff. Well, our thinking is moving along, if I can put it that way, from perhaps a simplistic viewpoint that every neutron star collapse produces gold from a supernova explosion, but that is possibly not the case. It might need colliding neutron stars to do it.
So all of this happened before Earth was formed, and as the planet was created, all of this stuff was just floating around and accreted into the crust.
That's right. For floating around, read interstellar medium.
Right.
That's the technical term.
Floating around.
Interstellar medium means floating around. Yeah, it's the debris between the stars, and a lot of that debris is the result of supernova explosions, and we're now seeing neutron star collisions.
Fantastic. All right. It's a really fascinating discovery and a major achievement. And if you would like to chase that story up, as Fred mentioned, it's the space.com website. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
3, 2, 1.
Space Nuts.
Our second story, Fred, looks at something just as spectacular, if not more spectacular. And we talked recently about finding the biggest, the biggest black hole ever, or it might have been the oldest. We found the oldest one ever. We found also the brightest cosmic explosion ever. Now we've found the brightest quasar, and this is also in conjunction with a huge black hole. The enormity of this is hard to comprehend.
That's correct. It is. The statistics are extraordinary. So let's do the statistics. This is an object with a very memorable name, J0529-4351. Don't forget that. It's intrinsically the brightest object in the universe. It has a luminosity equal to 17 billion times the sun's luminosity. I beg your pardon, that's the mass. The luminosity is even more. It's even more dramatic. Sorry, I've given you the wrong statistic. Its mass is 17 billion times the solar mass, so that makes it a supermassive black hole. Its luminosity is 500 trillion times the luminosity of the sun. Forget the billions, 500 trillion times the sun's luminosity. And all of this is taking place at a great distance in the universe. In fact, at a look-back time of about 12 billion years.
Wow!
So
that's
really
a long
quite
time.
Extraordinary. It is. So we're seeing this as it was when the universe was less than 2 billion years old. And the work has been led by Christian Wolff, who's an astronomer at the Australian National University here in Australia. And as you said, the story kind of starts at Siding Spring Observatory, where I used to work as the astronomer in charge of the Anglo-Australian telescope, the then Australian Astronomical Observatory. So they started with, basically, the story starts before that with an analysis of data from the Gaia spacecraft that we've talked about before, European Space Agency's Gaia satellite, which measured billions, and I think it's still doing it, billions of stars. So it essentially, in automatic mode, analysed this object as being a star because they thought it was too bright to be anything else. And the only real alternative to a star is a quasar. But then observations, at Siding Spring Observatory with the Australian National University's 2.3-metre telescope there allowed astronomers to recognise that this was not a star, but it was a quasar, and that it was bright, and that meant, and quasars are always seen at great distances, but the fact that it was bright meant that this might be a very special object. So applications were made to the European Southern Observatory for time on their marvelous facility in northern Chile, the VLT, the Very Large Telescope, which is actually 4 telescopes that can be used either together or singly, each one with a mirror 8.2 meters in diameter. And the only reason that these Australian astronomers could do that, could apply for time on this facility, was because of the strategic partnership forged between the Australian government and the European Southern Observatory back in 2017 that gave astronomers in Australia 10 years of access to the VLT, as well as access to the sort of governance of the European Southern Observatory and the ability to build instruments for them as well, things of that sort. So this strategic partnership, which is knowing about it is a big part of my job, Andrew, which is why I'm waxing lyrical about it at the moment. And it's not the first time we've seen classic examples of astronomers being able to capitalize on a combination of Australian instruments and the VLT, the Very Large Telescope. Only last year, we saw reports of the most distant fast radio burst ever discovered.
That's the one.
Yes, that was from discovered by a radio telescope in Western Australia, but identified as being the most distant fast radio burst at 8 billion light years away, or look-back time of 8 billion years, by the VLT, the Very Large Telescope in the Chilean Andes, the European Southern Observatory's facility. So that's the sort of backstory of the observations. But yeah, what a claim to fame that this object, the brightest, the most luminous object known in the universe. We've talked about boats for some time before.
Andrew, brightest of all time.
Brightest of all time, and I think this one might be. I think this is the new boat.
Yeah, the new boat. You mentioned the statistics. I don't know if you mentioned the size of the event horizon. This is just unthinkably huge. I don't think there's a word big enough to describe the size of this event horizon. This thing stretches 7 light years, which is 15,000 times the distance from the sun to the orbit of Neptune.
That's right.
15,000 times bigger than that. That's unbelievable. You can't get your head around it.
It is, that's right. And that's the kind of inner dimension of the accretion disk, which probably corresponds to the event horizon, exactly as you've said. And that accretion disk is, of course, what makes this thing bright, because this is all stuff swirling around the black hole, some of it being sucked in, some of it being redirected magnetically into jets to the north and south poles of the black hole, if I can put it that way. But all of that highly energetic and emitting light as well as X-rays and radio waves. So very, very energetic object. And I'm not sure whether I may have said this already, but it gobbles up the equivalent of one sun every day. 1 solar mass per day is what it's actually accreting. So I think it is also the most voracious known of all the supermassive black holes.
Now, correct me if I'm wrong. I have this distant memory that suggests that at this point in the age of the universe, quasars are all extinct, or am I thinking of something else?
Do you mean by this point?
What we're seeing now? Yeah.
Yes, that's correct.
We think so what we're seeing is quite historical data because of the time it takes for the light to reach us.
Yes, 12 billion years. This all happened 12 billion years ago. No, you're right. The nearest quasar, which is caused by a very active black hole, is actually less than 1 billion light years away. But there are very few within that distance. In fact, perhaps even only one, maybe even 2 perhaps, but most of them are more than 1 billion light years away, which means we're seeing them as they were before 1 billion years ago. And so today they're extinct. That's right.
So if we were able to just sort of flash over to this boat now, what would we see? If the quasar is extinct, brightest of all time, what would be happening there now?
So it probably will be, yes, in today's universe, it's probably a fairly quiescent galaxy, a bit like ours is. I mean, we think our own galaxy comfortable, warm and cozy place that it is for stars like the sun and its planets like ours, we think that may, in its history, have also been a quasar. There is actually evidence of outbursts from the center of our galaxy, from the supermassive black hole there, which probably caused by debris falling into it, quite significant amounts of debris. There's evidence of there having been jets because there's fluorescence of some of the gas above and below the center of our galaxy, which has probably been excited to fluoresce by jets of material, which are now long gone from the center of our galaxy. Jets of material that excited that stuff to fluoresce. The jets of material have gone, but the fluorescence is still there. So yes, maybe we think all galaxies might go through a quasar phase. I've always described quasars as delinquent galaxies, and it's not quite true because the quasar itself is the thing that's at the middle of the galaxy. The galaxy is just hosting the quasar, so it's more parasitic perhaps than delinquent.
Yeah. So they think this is the brightest in the universe. Do you think anything could top it? I mean, this thing just is gargantuan in size and brighter than anything. Like, the numbers are just staggering. Is there any chance we'll find anything?
Well, I think so. I think in astronomy, like many other things, never say never. There might be another discovery. This is a serendipitous discovery because this thing, as I said, was thought by the Gaia survey to be a star. And it was only because it was followed up as being an object of some interest by astronomers at the ANU, Australian National University, that it was discovered to be a quasar and then found to be a particularly interesting one. Yes,
fascinating. Yes, most definitely. Well worth reading about if you'd like to have a look. You can go to the ESO website, that's eso.org, and just do a search for brightest and fastest growing. And you'll definitely find it. It's a great story and a nice pickup from. I mean, the thing's been hiding in plain sight, basically, and
yes,
it's only just now we've pieced it all together. It's fascinating. Fred, just about to the end, I just need to remind people that if you're following us on YouTube, don't forget to hit the subscribe button below. If you would like to go to our website and learn about supporting us financially, you can do that. There's all sorts of options there under support space. Oh, hang on, what does it say? Now I can't remember. But anyway, it's there somewhere. Oh, look, support Space Nuts. That's what it says. So there you go. I was right. I should have stuck to my guns. So yeah, just have a look around and see what you can see. And if you want to support us, great. If you just want to be a listener, that's fine too. The more the merrier. That's we've got to keep the family growing. And Fred, that brings us to the end of this episode. Thank you so much.
Great pleasure. So, talk to you again soon, I hope.
Yes, indeed. And good luck with your goanna hunt. And
yes, it's
what worries some pictures.
Yeah, what worries me is that the goanna might be hunting us.
Yeah. Don't let the cat out.
Exactly. Oh, the cat, all right. Yeah.
Thanks, Fred. See you soon.
See you later. Cheers, Andrew.
Fred Watson, astronomer at large, and thanks to Hugh, not in the studio today, when AWOL. And from me, Andrew Dunkley, always great to have your company. Looking forward to joining you again on the very next episode of Space Nuts. See you then. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at bytes.com.
This has been another quality podcast production from bytes.com.